A fleet of robotic spacecraft is exploring the red planet, sending back a flood of data and helping to unlock the secrets of Mars. When NASA's MAVEN orbiter arrived in 2014, it became the first mission dedicated to observing the Mars upper atmosphere. This region is the conduit for air to escape to space, a process that may have dried up early Mars. The most likely cause of this process is the solar wind, a stream of electrically charged particles blowing from the sun. When the solar wind reaches Mars, it interacts directly with the upper atmosphere, piling up ahead of the planet in a bow shock. Charged particles from the Mars upper atmosphere, seen here in colour, fill the pole of the electric field generated by the solar wind. These particles, or ions, can pick up sufficient energy from the electric field to escape into space. In this simulation, green particles represent medium energy ions swept back in the wake of the solar wind. High energy ions in yellow and red follow the electric field in a polar plume above Mars. Now, data from MAVEN are supporting this model of solar wind erosion. This graph shows the first ever measurements of oxygen ion flux around Mars, allowing us to see the solar wind driving the atmosphere into space in both the polar plume and the tail regions. As the MAVEN mission continues, new measurements will be key to understanding how these processes operate, shaping the ongoing evolution of the Martian climate.
Mars has two moons, Phobos and Deimos. Both are small, airless bodies with irregular shapes. To better understand these moons, scientists at NASA's Goddard Space Flight Center simulated the solar wind environment at Phobos. Phobos orbits incredibly close to Mars, only 3,700 miles above the surface. In fact, it whips around the planet in less than 8 hours. Because it has no atmosphere or magnetosphere, Phobos plows directly into the solar wind for part of its orbit. The solar wind consists of negatively charged electrons, which are light, and positively charged ions, which are heavy. Normally, they exist in equal numbers, so the solar wind is electrically neutral. Phobos, however, absorbs the solar wind on its day side, leaving a void over its night side. Because the electrons are lighter than the ions, they rush in to fill the void. This creates a field of negative electric potential over Phobos and statically charges its night side. The ions are attracted to the field and pulled in farther downstream, restoring the solar wind's density and neutral charge. The simulation also looked at a massive crater called Stickney. It showed that when Stickney falls into shadow, electrons initially move into the crater, and the associated electric potential forces the ions to keep up. On the smaller scale, this electrically charges the crater interior through the same process that charges the larger night side. Phobos is often cited as a target for future exploration, but roving around on the night side or within shadowed craters could build up static electric charge, possibly affecting sensitive equipment. Mission planners will have to face this challenge as they set their sights on the moons of Mars.
I'm Glyn Collinson from NASA's Goddard Space Flight Center, and I'm here to tell you today about the electric wind of Venus. So Venus is cool. Venus is awesome. Venus is, in many ways, one of the most Earth-like planets that we know of. So just as every planet has a gravity field, we think that every planet has a weak electric field. So we went looking for Venus's electric field, and boy oh boy did we find it. It turns out that Venus's electric field is at least 5 to 10 times stronger than at Earth. It's a monster of a force. It can rip heavy things like oxygen straight out of the upper atmosphere and send them kicking and screaming off into space. So this really changes the way we have to think about planets, because it turns out that planets can lose heavy things like oxygen to space entirely through electrical forces in their ionospheres. This is something that's really important if we want to go looking for exoplanets, for habitable planets around other stars. It is no good having conditions perfect for an ocean and an atmosphere that you might want to breathe if some invisible force is going to come along and rip it all off into space. Only understanding how atmospheres evolve can we try and understand how we got here.